So my name's Isaiah. I've got Lorenzo here. He's the voice of the customer. He's going to speak shortly. When we talk about primary storage, enterprise storage specifically, there's a few things. I shouldn't turn my head. All right, cool. There's a few things actually that we keep in mind. First thing is we programatize this. So at AWS, so I work in the partner team. I work with storage partners. Not just customers, there are in fact storage partners in the audience. If you see one of your storage partners, you should reach out and say hi. So when I say we programatize it, we're trying to shortlist what's good. There's so much stuff out there. How do you know what's bunk and what's awesome? And so we have a fairly lengthy validation checklist that includes a lot of customer references. It includes historical information like how many customers are using it and how much stuff has been written to the cloud with it. And so the logos that you see up there, which will probably, that list will probably change even by the end of the year, are solutions that we shortlisted. In fact, one of my favorite ones isn't even up there. So if you don't know what the ways to access primary storage are, we'll first talk about sort of the differences between things like object and block and file. What's a block? Well, simply put, it's a chunk of data. It lives on a block device, and software manages it. Now, that software could be a file system, it could be a database, but it's managing all the data for you, and it's doing it in sort of a microscopic fashion. It's not a macro level thing. It's very down in the weeds. There's no metadata generally about blocks, unless you put it there. You can layer metadata on top of a block with things like software. File systems do that. But you yourself as an end user wouldn't do that. So generally speaking, block interfaces aren't so useful in the cloud, except for things like operating systems and maybe some databases. So when you think examples of block interfaces, those would be things such as if you have like an iSCSI appliance in your office, the flash in your phone, or the drive in your laptop, the hard disk in your server. EBS volumes are block interfaces. And when we think about enterprise storage, there's other things that come to mind too around data replication, data governance, durability semantics. There's a lot more to it than just putting the bits down on the disk. So files are also chunks of data, but I think as everybody probably knows, they're embedded in a hierarchy. That hierarchy is a file system. And so that file system keeps track of the things that are on a disk, for example. But if something bad happens to that file system, its reference points to the data that it's written down might be lost. So file systems, they were good for like 30 years. And then we had so much data, we meaning sort of, the royal we, all of the AWS customers especially, humanity, I guess, as a whole. We had so much data that we started to lose it, and so we needed new ways to track data. So objects are more than just a bit of data that you access with a REST API. In fact, there's object systems out there that don't have REST APIs. The object model actually goes back quite a ways. But the significance of an object is, the way that it's being written down is a way that ensures that it's not going to get lost, and that's super important. The more data you have, and there's more data than ever, you don't want it to get lost. And B, that you can apply semantics to it in ways that you never could with things like files. For example, the immutability of data has all kinds of implications in things like S3. It means that you don't have, yes, you can't go and edit something, right? You have to go put another copy of it. But it also means that keeping track of whether or not it's been, changed or something like that, or protecting it against corruption gets a lot easier. From a latency perspective, the way you interact with things like block and file and object are worlds different from each other. The time frame by which you would operate on files and blocks are very, very small. The time frame that you would operate on objects is much larger by comparison. It's still very fast, but it's much larger by comparison. Snapshots are a feature that enterprise storage sort of assumes everybody has. At this point, if you don't have things like snapshots and clones, it's entirely likely that you, are using something like, I don't know, ext4, or even ext4 has snapshots. You would be using like 90s technology, like early 90s, not even mid 90s, if you had a file system that didn't have things like snapshots, and then late 90s if you didn't have clones. So snapshots are a way of sort of tracking the differences between 2 points in time in a differential way. And so that the way that they work, and we'll just build this out, is you start off with something, let's say two blocks or two pieces of data, chunks really. And when you take that snapshot, you store that chunk somewhere. It could be the same system, it could be the same, oh, thanks Leron, appreciate that. It's somewhat embarrassing, somewhat hilarious. So you store those chunks somewhere. So there's technologies today that can store those chunks in S3. And in fact, even EBS, the way EBS works when you take a snapshot, it reduces what you had in your volume as much as it can for efficiency's sake, and it stores it in S3. Why does it do that? Well, the durability in S3 is so much greater than the durability of other things like local disks, that sort of thing, and EBS. So then when you make a change, you delete block 2 and you add block 3, and you take a second snapshot. Chunk 3 goes into your sort of snapshot storage area. So now you have 3 chunks that you're keeping for long-term retention, and you still have 2 chunks or 2 blocks that are live on the volume. So this may be remedial for many of you, but everybody seems to be looking up, so hopefully it's engaging. And then let's say you add a 4th block, and you take so now you have that chunk, and let's say you delete the first snapshot. So the first snapshot had chunk 1 and chunk 2. So when you deleted the first snapshot, the thing that was unique to that snapshot, which was chunk 2, goes away forever. So why is this important? Because people live and die by these technologies. It seems simple, like a rudimentary thing. But imagine not having it. Imagine life without snapshots, without the ability to take quick copies of data. It's not really a backup in the truest sense of the word because it's not searchable and indexed and subject to hold and all those kinds of backup terminology things. But it's, but if you didn't have snapshots, it would be pretty hard to live life in computing these days. Even your Macs, right? I see a sea of silver out here. Your Macs have snapshot capability built in. EBS volumes have snapshots. Versioning in S3 is a form of snapshots. So the way that snapshots have sort of eked their way into our life is pretty substantial. But what can you do with it? Well, one thing that you can do with it is, because snapshots tend to be fairly lightweight in most systems, you can instantiate new copies of that data in a read-write fashion pretty easily. So here's an example of how that use case might look. You got a bunch of live volumes on the left, and you take a snapshot. So now you have data that's stuck at a point in time. So how can you, as an enterprise, take advantage of that? You can now create a clone directly from that snapshot. So this is how most people use EBS snapshots. This is how anybody who's ever been a NetApp customer uses Flex clones. This is how almost any system that is an enterprise storage system operates. And when you have the ability to take thinly provisioned, low overhead clones that are fairly instantaneous, because maybe the snapshotting methodology is instantaneous or the cloning methodology is instantaneous, it opens up a huge area for people from a dev and test and QA perspective. It's really common to see people have one, let's say, production volume, maybe they replicate it somewhere, take a snapshot, replicate it somewhere, and then they might have 100 clones or 100 volumes based on that snapshot. If you're not doing that today in your environment, I would ask the question, why not? Like, how is it that your process isn't built around these kinds of low-hanging fruit elements? It's a really easy way to make sure that the stuff that you instantiate in a new environment is an exact replica of what you've got going on in production. Maybe you have to sanitize the data when you get it there, but it's usually it's pretty quick. So the benefits, we'll build it out so we can just talk about all of them. Great. In most cases, snapshots are instantaneous. What that means for practical purposes with things like EBS volumes is that for the first one you have to wait, but for the others they're differential and they don't take anywhere nearly as long. If you're using something like ONTAP Cloud, it'll be instantaneous. If you're using Weka, it's instantaneous. If you're using SoftNAS, it's instantaneous. All of these things were built around the concept of it's got to be point-in-time consistent, and we don't want to interrupt ongoing operations to the file system, so therefore we have to be clever about the way that we're sort of stopping the world, keeping track of what was there at that moment in time, and then letting things move forward. They tend to be fairly space efficient, even in EBS. EBS volumes are deduped and compressed, not to the extent that you would get out of like a data domain or something like that, but it is there, and that savings is passed on to customers. In things like Waffle and in other technologies, space efficient means that when you create a clone, until you start changing stuff in the clone, it occupies 0 space. There's a little bit of overhead, a few bytes here and there, but even deleting things occupies more space than leaving them there, because it's an exact copy of the way things were. You could think about it like the way that some links work on file systems, that having a link doesn't actually occupy 2x the space. It's the same block that the links are pointing to. It's just 2 pieces of data that are pointing at it. So then when you change something that's in the clone, the storage technology says, okay, well, now that's a new piece of data, and I'm going to go write that freshly. And then lastly, whether it's a partner solution or a native EBS snapshot, the ability to replicate the data where you need it most is readily available. The next thing that I want to talk about with regard to enterprise storage is understanding how people have traditionally deployed things and why it doesn't work. Traditionally, you would see, and you still see this stuff today, like I talk to customers all the time running like SAP environments, and they're like, okay, we've got this RAID 10 over here, and it's doing synchronous replication to this other RAID 10 over here, and that's doing async replication to this other RAID 10 over here. And they think that they're protected, but they're not. So why aren't they protected? Because probability is not fun. And the probability of failure has to do with how many fault domains you have and the mean time before failure of each one of those individual components. Just because you have a mirror of something doesn't mean that you're safe, because mirrors are actually implicitly requiring that when you do have a failure, that you be able to rebuild. And the fault domains across all of those things, those 6 RAID 10 components, don't have any way of knowing about each other or being clever about how they recover from failure. So we'll start with MTBF, which is really a problem of locality. You have bandwidth allocations for recovering from failures. You have time overall for how long you can be down before statistically you might have another failure. And so the myth is that mirroring plus synchronous replication will get you where you're going. The problem is that, let me move to the next slide. If you have a failure there, your durability is reduced in your primary. What that means is that now you're no longer redundant, and if you suffer a failure there, whatever is using that RAID 10 LUN or array is not going to work anymore until you're done rebuilding. It's not like you can get 80% of the way done rebuilding and you're good to go. You have to get to 100%. So how long does that take? That's one question. And the second problem is that there's nothing that says that you have to suffer an additional failure in the same locality area. It's entirely possible that you could suffer the next failure in a different area, a different fault domain. And what that means is that now you have 2 environments. Neither one of them are redundant. And you have to rebuild both of them before things are going to be OK. If the next failure that you were to have would be one of those 2 synchronous replication points, now this is durability, right? But at the point that you suffer an additional failure in one of those synchronous replication points, you now have an availability problem because you probably have applications that are expecting that storage to be there. So those systems, they don't rebalance across each other. They're not smart enough to know that they can't suffer additional failures. You have to know. You have to be smart about it. And that asynchronous backup isn't coherent, and that means that things that are written to those synchronous replication points aren't immediately written to that third one. So now you have a sense for why it's important that the stuff that you're using be smarter than technology that was invented back then. It was good for then, right? But the more data you have, the more data you have to rebuild. And so in today's world, with enterprise storage systems that are supporting workloads like enterprise stuff like SAP HANA is a great example, right? You need like 1.5 or slightly less than that times disk of what you have in memory. So if you have a 30 terabyte system, you might actually have to have something on the order of 40 to 45 terabytes of disk. And you not only have to protect what's on that disk, but the I/O has to be super low latency the entire time, even when you're trying to do a rebuild. So I can't think of any more quintessential enterprise requirements than things like that, where no matter what's going on, performance has to always be absolutely amazing, and you always have to make sure that it's available. So what's the difference between availability and durability? People often talk with storage vendors, and storage vendors will conflate the concepts into what they would just simply call reliability or resiliency. But we tease them apart at AWS because and if you push them, they'll tease them apart for you as well. Availability is, when I try to talk to it, is it there? Durability is, did it lose my data without meaning to? So we talk a lot about S3 having 11 nines of durability. That's what we mean. We mean 1 in 100 billion chance that your data is going to be lost. In fact, S3 has never lost an object inadvertently. People have deleted stuff that we've helped them recover, and sometimes it's been too long, couldn't help them recover it. But it's never inadvertently lost an object. It's got trillions of objects, many exabytes of storage, and it's never lost any customer data. So that's super important because that means that we've actually beat our design. Our design was up to 1 in 100 billion chance. We have many, many trillions of objects, so we've beaten our design if we've never lost anything. When you look at the probability of loss for a typical enterprise solution, that's 5 nines. 1 in 100,000, I mean, what if those were blocks, 1 in 100,000 blocks? It's 100,000 things, right? So it could be disks, wherever your fault domain is. It could be disks, it could be slices of disks. There's a lot of systems out there that will actually partition disks and treat each one of those slices as a fault domain. With Flash, it could be portions of the physical topology of the memory. Versus availability. 5 nines of availability means that your unplanned downtime per year is 5 minutes and change. So those concepts are related to each other, but they're not the same thing. And so when somebody says to you, oh, it's designed for 6 nines of resiliency, you want to ask the question, is that availability or is that durability? Because there's a pretty big difference. 6 nines is pretty good. I mean, that's 31 seconds per year of unplanned downtime. I mean, that could be a VIP failover, right? From one AZ to another. That's fantastic. That's actually not bad. Good availability. Enough for most enterprise applications. But 6 nines of durability isn't good. And the reason it's not good is something that I'm going to go over in the next few slides. So when we talk about failure, if we talk about MTBF, if you have something that fails every 1,000 hours, and that's a reasonable number, manufacturers will tell you things like, oh, this drive has millions of hours of time on it before it will fail. That could be true. My experience has been that things fail a lot more frequently than that, and that there's a lot of variation in failure rates. There's good data out there that you can look at for yourself. But let's just assume that it will fail every 200,000 hours for the sake of argument, which means that every 22 years that thing will fail. That's a long time, but the way that probability works is that if you have a lot of something, it compounds. So let's imagine that it takes you 8.5 hours to repair, but you have 12 of those things. So now, because you have 12 of them, you're looking at the probability of not 1 over 200,000 hours, but 12 over 200,000 hours, and it's a much larger number. If it takes you 8.5 hours to repair, that means that during that 8.5 hours, the probability is now different. It was 12 over 200,000. Now it's a different number for your sort of remaining durability. So while that node is out of service, for example, or while that system is down, all of the other things are also accumulating I/O. They're also accumulating the probability of failure. You may remember that when RAID was created, initially it was mirroring, and then it was like parity-based rebuilds. And then not long after that, there was this concept called double parity RAID. And so double parity RAID meant that you could have failures, and that was good. And then some other technology said, well, we can handle 3 failures, and that was great too. 3 failures is pretty unlikely, though. The probability of 2 failures with a 200,000 hour MTBF is that while you have the first failure going, every 4,000 years, 1 out of every 2,134 repairs, you'll have that second failure. So anybody ever had 2 drives fail at the same time? I have. What does that tell you? Probability is just probability. So anybody ever had something take too long to rebuild and you had another failure in the middle? I have. Anybody ever had a UPS truck carrying your tape catch on fire? I'm not kidding you, there was a guy in another session yesterday that actually happened to him. It was just a drill, but that means they passed they failed their tests. So that's actually never happened to me. I hope it never does. If it was on tape, it should be on Glacier. So the third failure probability is really unlikely, and so that's why, realistically, and not a lot of people architect for it, but that second failure probability is super important. But what's actually really important here is that most software isn't smart enough to prioritize the bits that are broken in a way that would help you rebuild in an optimized way. There's some stuff out there that is smart enough, but most stuff isn't. And if you were going to go do, let's say, software RAID, for example, in Linux or something like that, it wouldn't be. So there's these are sort of real scenarios. So these are the things that enterprises come to us and they say, these are the things that keep me up at night. They keep me up at night because I need snapshots to make my workflow better. Things like snapshots and clones make my business more efficient. I need to make sure that I've replicated my data in a way that it's intelligent. I need to make sure that I've got storage systems that are going to be smart about rebuilding stuff, because it's fine to manage one system in the cloud, but what happens when you're managing thousands of systems? What happens when you're managing tens of thousands of systems? It's not scalable if you have to manage it yourself, right? As anyone will tell you, when you have more of something, you tend to notice that things break more often. So the reason I wanted to talk about that is because when our customer comes up, they've actually, Lorenzo has built into his workflow a lot of the things that enterprises tell us that they need. And we actually tell those enterprises, it already exists, you can use it, it's out there. You just have to change your workflow a little bit to take advantage of it. And so without any further ado, I welcome my co-presenter, Lorenzo from AWS Media.
Good morning, guys. Good morning, guys. So my name is Lorenzo Donina. I'm a cloud solution architect. AWS Media is a software house which was founded in 1999 in Milan, Italy. And right now we have branch offices almost everywhere in the US, UK, Australia, and China, and Brazil. Who we are? We develop, build, ship, and deploy, and scale, and manage a software solution for complex mission-critical environments. We create software that allows a producer and journalists to create, search, customize, and deliver any kind of content to almost any destination, from the real paper to the web, to the mobile apps, push feeds, and whatever. Who are our customer? Our customer are a major news media organization and a financial institution that unfortunately are not listed here because they don't want to be listed. And we are currently extending also our presence in other verticals such as pharma and banking. So the challenge that we were facing at the beginning of this project, which was 3 years ago almost, was being able to improve the content delivery for all of our customers and let them publish things constantly within milliseconds to several destinations located in several AWS regions. We wanted to automate the deployments and let the developers create, deploy, and scale storage system without filling up tickets and wait time. And also we wanted to move all of our on-premises deployments that were based on a traditional bare metal infrastructure and VMware environments to the cloud. We decided to go with AWS, and also we wanted to optimize the way we consume data. Before we were using a system to predict how data will be growing during the time, so we were thinking about, okay, this aggregate is not going to be enough in the future, so we need to buy new arrays, new disks, and we were using some specific software to make sure our calculations were correct. And we want now to being able to actually expanding and shrinking data without, to plan things in advance. So NetUp on cloud, we were using NetUp on cloud for HA. The first thing to synchronize data between ONTAP on the physical world to the ONTAP on AWS. We were using some function of NetUp. From one function, which is the most important, was using SnapMirror. We wanted to use SnapMirror for doing this since we used that for compressed data and make sure that data transport will be encrypted end-to-end. And when you have to migrate terabytes and hundreds of terabytes, having a feature like SnapMirror is great. We wanted to create a multi-site and disaster recovery site. So we wanted to leverage on the SnapMirror also to sync, of course, in a synchronous way to other storage located on different regions. For example, we were running primary in US East 1, and we wanted to being able to build a DR on another region, for example, Oregon, and keep them in sync using SnapMirror. The other thing is that we wanted to being able to recover from a failure within seconds without need to pre-warm EBS. A pre-warm is every time you create a snapshot on AWS, all of these snapshots were stored on S3. And if you create another volume which is based on the, which is created starting from a snapshot created before the ABS will perform exactly as a baseline performance, if it's a GP2 or if it's a IO1, you got to pull every single block. So since we don't want to wait time before the EBS actually perform as we need, we decided to use NetUp for this. So we can just cut over from one node to the another node in seconds, and then the performance that our system will aggregate would be correct and stay to the baseline. We also wanted to move some legacy apps to the cloud with almost zero effort. So we can still leverage on iSCSI and NFS without need to re-engineize the application entirely. We wanted also to leverage the AWS capability for the instant provisioning. So we can create an aggregate based on EBS disks, decide which kind of EBS we want, and then we can live migrate volumes on it, and then we can do whatever we please. If the volume we can extend the volume, shrink the volume, move the volume to another aggregate, so change the aggregates type, and do all of those things live without service interruption. We also want to leverage the space efficiency feature of NetUp, such as the compression, the duplication. When you have to deal with hundreds of terabytes of data, having all of those features will let you save some real money, and my manager was very happy about it. And we also wanted to use NetUp on cloud for increase the DevOps agility. Before we were having tons of tickets from our developers in every single office asking for, I want to have a new volume, I want to attach this volume to this and the other machine. And now they can do this automatically without any request, any more ticket. And also we want to take the advantage of the cost effective of the flex clone, thin snapshot, and all of those things. When our developers want to test something with some real data, we need to provide the same data set that we're using in production. And if you have to do this and you can leverage on the flex clone, you can immediately create a volume based on a snapshot that you created the day before at some specific time. And then you can export this volume, and all the machines which are to this can access this volume immediately without wasting any space. And space, of course, means money. So what we implemented, We're using on-top cloud for AWS in the availability layout. Basically, you have two EC2 instances that are located on two different availability zones. They sync data between each other in a synchronous way. So it's not an async feature like a Snap mirror, but every single block has been committed to both heads at the same time. And the aggregates where we store the actual volume are located on EBS disks. So we can create an aggregate based on some specific kind of EBS disk, and we can dynamically add new EBS to extend this aggregate, and we can do this just using a RESTful API. So how it works? Basically, for the iSCSI connection, you can leverage a multipath. So basically, you establish two permanent connections on both heads at the same time. And the multipath system is able to understand when one path goes down, and you can set a priority. And if the one node will fail, automatically the multipath will keep providing service to the application. What about the NFS? NFS is an old protocol. It doesn't support these kind of things. So it works this way. Basically, you create a floating IP, which is no part of the siege of the VPC. So it's cool. It's a fake IP. It doesn't route, it doesn't do nothing. And then you control these using the VPC routing table. So, for example, let's imagine in this slide here, it's represented what is going to happen if the node will fail. So if this node will fail, the mediator, which is another component, will realize that the machine has failed. And then will interact using the AWS API for changing the reference between this floating IP and any interface of the instance. So basically, the IP will still the same and will float between those two instances and using the AWS APIs. This is controlled by these very small instances that we suggest to locate in another availability zone. In this case, we are using B and C, and mediator is located on an availability zone. It basically keeps constantly checking if the instances are alive and if are able to perform, and instruct the system to switch over to one node and to another node. To deploy all of this stack, we've been able to accomplish a few results. We've been able to move workloads from the cloud to the NetUp data fabric. We are currently, for example, we have a mixed layout. So we're running some customer in production on AWS, and we are mirroring back to our on-prem storages. We're running some customer on the virtual infrastructure, and we are mirroring on the cloud. And even based on what we need in terms of performance, we can just move workload from the cloud and back to the on-prem, and even from the cost perspective. So we can decide to spin up some SD1 disks on AWS and store some data on it, and then the week later we can just go back to the on-prem. We want to keep having this choice. We want to be able to decide what to run on AWS, what to run on the cloud, and what to run on-prem. We've been able to use the elasticity and the speed of the cloud for the on-top environment because it is very easy to create new storages. You can just deploy storages in less than 15 minutes, and you can access directly an SSH into, spin up some volume, destroy these volumes, and our developer love it. Basically, they just fill up some JSON, and they show this JSON to a REST API, and then after 15 minutes, you got an entire stack which is online. You can SSH into there, and you can do whatever you please and destroy later. Also, you can control these and schedule for shutting down automatically, for example, during the weekend and during the night, and save some real money on. So no more waits for weeks and days to do this. What we're planning for doing, what we're planning for the future, well, we want to use the on-top and Trident integration with Kubernetes for integrate the persistent volume framework. Our latest applications are based on containers, and we orchestrate that using Kubernetes, which is an open source product of Google, which is pretty awesome. And we want to federate cluster from the cloud and the on-prem, and being able to decide, okay, now this application is going to run on Kubernetes on AWS, now it's going to run on-prem, and we want to be able to move back and forth whatever we please. Also, we want to use this to distribute and scale data approaching multi-cloud deployments. Even if AWS is awesome, it's not the only player around. So we want to be able to decide on which specific cloud provider we want to run our workload, in which region, and we want to decide based on several conditions, data center location, if proximity thing, and all of those stuff. Now I want to go through a very quick demo. Is about how easy it is to deploy and create a stack. Okay, so this is the Cloud Manager interface. So basically, you can create let's see, sorry. Okay. So this is the Cloud Manager interface. So it's the interface that you can use to create new environment, upgrade this environment, making sure the replication is working fine, and do some operation like increasing the amount of EBS that are composing and aggregates and doing all of those kind of things. In this demo, we spin up a new instance on AWS, on a US region, and we are connecting this externally using a public API. Of course, I'm suggesting you guys in production how to do that. Basically we can, this is the interface, and now I'm going to show you how it works. And there are several tabs. My name in this case is Michael Jordan, of course I'm not. And I'm going to create some of those, and I will interact to AWS using the CLI. Of course, all of the things that I'm going to do using the CLI are possible to be accomplished even using the UI. But I don't like it that much. So we're going to go through this. So this is the OCM. Is a T2 medium. Is currently running. We're connecting over there. And you can run this on an existing machine. It doesn't matter if it's located on AWS or it can be on your private cloud or in your VMware environment. It can be in a container or whatever you please. And then you can access these externally. This is the IP, and which is the same IP that you're seeing right now. As I said, you can control several storages. You can create tenants for each of them, and you can also do other things like configuring the LDAP and tenants account. This is the demo tenants that I created. You can control the replication, and you can set up several things. You can set up the encryption, and you can also configure this for login using your existing LDAP server. Here you have the encryption setup, so you can set for using KMS or even an external encryption system that you guys may have. And it's important that you need to configure inside the Cloud Manager the credential for AWS. The on-top Cloud Manager needs to communicate with AWS, and it needs to do this using the API. So you need to create a specific user with a specific role, AM role, and then those needs to be configured inside this. So now let's start trying to do something, and let me first understand. Let's describe the VPCs that I have in this very account in here. I'm using Profilan since I have several profiles, and okay, we have several of those. Let's copy this one, which is VPC for QA, and I'm gonna set these into a variable. So we're not gonna type it again in the future. Okay, this is saved. It's important to save this into a specific variable to do not need to constantly type it down and doing all of those things. So let's copy this over and then wait till completion. Okay, now let's describe the VPCs on this. Sorry, the availability zones. So now let's describe the availability zone. As I said before, we need at least 3 availability zones. We want to locate one node in one availability zone and the other one in the other, and the mediator in a dedicated availability zone. We don't want to have the controller system in the same availability zone of what we're trying to control. So now let's create a keeper. We need a keeper because it's going to be useful later for configuring into the on-top system. We're going to create a key for the nodes. We're going to now use a query and save this into a PAM file. We are going to use this PAM file later for SSH into things. We're going to do the same for the mediator. So we want to have different SSH keys, one for the nodes and the other one for the mediator. We're going to do the same again with the profile, and we're going to query again and use the key material key material, and then save the output again in text and call it on top mediator.pem. Then, okay. Then, it's now time to create some keys. ONTAP supports KMS, so you can create some keys, encryption keys dedicated only for your specific ONTAP system. Or you can, as I said before, you can rely on external system. So if you want to already have an external encryption system and you want to use that, you can. Or if you want to use the KMS, you can just create a KMS key. So let's create a new key. We're gonna call description. Okay, it's gonna be called ONTAP, and we're gonna use the profile amp. Next time I will save the profile as default. And okay, now let's create an alias so we don't need to remember the ARN. Okay. Here we go. This is the alias. Oops. And then the ONTAP, and we're going to target this key ID and copy this over. Profile, and great. Okay, so now let's clear this shell out. Okay. All right, so now that we have this KMS key and we have almost everything we need, we can proceed doing this. So everything that I'm doing right now using the UI can be performed in shooting an API call and providing a REST, a JSON file. We can deploy a single ONTAP on a single availability zone on an HA cluster. Now we want to use the HA cluster, so let's click on this, and we're going to then provide some details. First of all, the name. So this is going to be ONTAP HA, and then some tags, for example, the environment, which is going to be test. Okay, and then some username and password. Okay, now we need to select the multiple availability zone on a single availability zone. So even if it's an HA cluster, it can be located within the single availability zone. So of course, it will not protect against availability zone failure, but it will protect against EC2 failing. So in this case, we're going to select the multiple availability zone, and so we can just click on this, or you can even click on extended information if you need more from this. It's important to understand in which, of course, region and VPC we want to spin it up. So let's copy this from the previously. So we're going to use Orland, and this is going to be the default VPC. It's been automatically completed because it's the same VPC where we're running the Cloud Manager. Now we can select to use a default generated security group or select some pre-existing security group. All of these things will then produce a CloudFormation template that will be automatically sent to AWS, and the machine will automatically spin up. So in this case, we will select the automatically generated security group. We will locate the node 1 in the West 1, and we're going to use the same subnet here, B for the node 2, and then the mediator will be located on C on a specific subnet. We can now click on continue. Now it's time to select which kind of authentication and we want to use for the mediator. You know that before I've created some specific keys only for those machines. So we can select key and select the keys that were created before. For the purpose of this very demo, I would like to use the password so I don't have to copy it over the SSH keys over to the machines. So don't do this in production, never. But I'm going to do this on this very demo. The same for the mediator, we're going to use the ONTAP mediator, and then we can decide which kind of internet connection method we want to use. So we can associate an ephemeral IPv4. We can use a proxy if you have a proxy in place, so or we can use a NAT gateway if we want to. My suggestion is to use a NAT gateway because you're going to get rid of all the other implication in having a public IP in something. But for this demo, we don't have any NAT gateway. So now we need to specify the floating IP. Those IP IP must be outside of the seed block of the VPC that you guys have. So you can just use some random IP, just make sure those are not already present in your VPC. If you have a huge account, a large account with several VPCs and several networks, and your network guy will complain with you about several things, then it's better if you just double check before creating, because you may end up in doing some disaster. In this demo, I will just use a random IP, and let me check which one I can use. Floating. All right. We need one for the cluster management that we'll put in here, one for the NFS for a primary, and the other one for a secondary node. I'm going to use this. The system will automatically make sure that this IP is not inside the VPC and is not already configured inside the VPC routing table. So if it is already present, you will then receive an alert. This is the explanation about how it works. The cloud is, for the iSCSI, as I said before, is using multipath, and you can control using existing unit. Then it's time to select the routing tables. In a real environment, you will have tons of routing tables. In this demo, we just have one. So it is pretty easy to select which one we wanted. For the next, the system will perform the check. So this is the routing table. Let's click on it. OK, so unfortunately, the IP that I selected before are already used somewhere else. So let's change it. Let's change this number and 6 and 7. OK, now time to select which kind of encryption we want to use. So the cloud management is if you already have an external encryption system. We don't. So we're going to rely on KMS. And then we're going to select the keys that we have created before. We created an alias for the on top. So now this is the license things. In this case, we're not going to use the bring your own license. We're going to click on no. And then we need to select which kind of pre-configured package we want to use. We can also customize this. Those are intended in which kind of machines you have, and which kind of disks, and the instance tenancy. Of course, it's not only about how much memory and CPU the machine has. Every single instance family has a specific throughput to the EBS volumes. So make sure you're going to select an instance which have a specific amount of bandwidth through the EBS. EBS disks are network disks, so you're going to make sure about this. Also, if you want to use the on-top supports, if the system is the clients and even between the nodes, it does support jumbo frames. So on not all the AWS machine does support jumbo frames. So make sure to select a machine which has this support. NetUp already provided you a few examples in like cost-effective for the DR, if you want to have more performance and all of those things. You can check all of this information. For example, in the case of M24X large, you can select details and click on this, and then you will see that this machine, for example, as 832 is an EBS, and then you will even be able to understand the dedicated bandwidth to the EBS disk. So make sure to select the right instance, because this is going to improve performance and is going to do a real difference in the production workload. So now let's click on one of those settings. Let me see. We're gonna select. Okay. I don't know. Go to this. Okay. This for 8 terabytes. Another thing which I forgot is make sure even to select the right group of EBS disks. For example, not all the GP2 disk has a baseline performance. It depends on the amount of the space. You have a ratio between the space and between the performance, so make sure to use that. This is also something that you can use for creating volumes and select the volume protection. But in the purpose of this demo, we don't have all of this, so let's skip it. Now it's time to review. We have a HA. We're running 9-tour C1. We're going to use GP2 disk, an 8 terabyte. We're going to use this VPC on a multiple availability zone. We selected the management floating IP and license type. Master keys and write speed is normal. We can also use some IO1 disks as a cache. Now let's click on this, and this is the API call. So of course, you don't have to go through this procedure every time. You can just fill up this JSON file and then use it and show them using the REST function. What we do internally is we compose and we create these using Terraform or Ansible, for example, and then we just show them to the end. So when we click Go, I'm going to show you what is happening on the other side. The user, which is Michael Jordan, is using this access key and this account ID to perform all of this operation. So what is happening on the AWS side is that the CloudFormation template has been generated, and the connectivity is the first part of the procedure, and in 50 minutes after you perform those clicks, you will be able to access the system, and you will be able to create something, scratch the system again, or clone it to another system which can be identical. As you can see, in a while, few machines will start, and then in about 15 minutes, you will have an entire system up and running. Thank you so much.
You guys get all that? Lorenzo speaks English as fast as he speaks Italian, I think.
It's not true. I'm sorry for my broken English, by the way.
It's okay. I think your English is better than my Italian, so accept that for what it is. So we, yeah, all right. So we have some additional resources here from links for you. There's also a new training curriculum, new storage training. Over the last several months, the training team has been putting together with subject matter experts across Amazon, people with expertise both for on-prem things as well as native in the cloud things, trying to figure out, we've got training tracks for all kinds of things, but not storage. So they've built a storage training curriculum. And so the intention is that when you go through this training, you'll have an opportunity to dive deep with good quality materials on all of the native services so that you'll know how, for example, to take advantage of each one of their strengths and use it to your advantage. The way it's often the case is that customers will do a little bit on their own, and then very frequently they'll go off and they'll maybe use a third-party product or a partner solution. This is especially true when we start talking to our consulting partners. The practices that they build need to be repeatable. And so making sure that folks have the same training everywhere is a good way to help increase the likelihood of those repeatable businesses. There's a lot of opportunity, I would imagine, for questions. Feel free, at least I'll stick around. Feel free to ask them. We also have lots of partners in the audience, so if you guys want to meet each other, it's quite cool to do that sometimes. One of my favorite partners is actually a company called Weka.io down here. If you have high-performance enterprise storage stuff, especially the high-performance part, you may find it interesting to speak with them. So thank you very much for sticking around, and I hope you guys enjoy the rest of the week at reInvent this year.